I'm not in period 3.
Okay, good. All right, because then maybe you didn't homework. All right, so it's like this. You started taping?
Yes.
All right, welcome. This is, because we've had lots of snow days and we need to learn calculus, we're doing a special makeup lecture which Antares is videotaping. We have some 6 or 7 people here and we're going to treat it like a normal class. We're going to go for about an hour and then everyone's going to watch it. So let's do it. Bunch of things. First off, last class we did some derivative rules. In fact, there are a whole bunch of derivative rules. And so let's talk about some of them now. You may have seen them in the textbook. And some of them are really, really obvious. For example, what is the derivative of a constant function? Well, what do we expect the answer to be? Yeah, 0, because the derivative is like the rate of change of a function, and a constant function is not changing, so we think the derivative is 0. Okay, we can prove this. How should we prove this? Let's do it. Follow the rule. What is the formula for the derivative of a function? Yeah, I'll start. It's the limit as h goes to 0 of f of x plus h minus f of x all over h. Just do the same thing every time. Okay. Well, in this particular problem, what is f of x plus h?
C.
It's just c, right? So, because that's how constant functions work. They just output c regardless of what you input. And f of x is c. So, what kind of limit is this? Oh. She says that this is a 0 over 0 situation. Is that true?
Looks like a little bit.
Sort of. No, actually I tricked you. It's not a 0 over 0 situation because what is a 0 over 0 situation?
It's when something close to 0 and something close to 0.
Yes, it's when the numerator and denominator are both very small. In fact, this is what is this? This is just
0.
This is actual 0, okay? Yeah, this is actual 0 over h.
Yeah.
So it's actually not a 0 over 0 situation. It's an actual 0 over an almost 0, and then therefore, what is this limit?
0.
Is 0. Okay, so that's how we proved a little fact. There's another kind of fact we can prove. What is the derivative of just a constant function? Oh, by the way, have I used this notation yet in class?
We just saw it in the book.
Yeah, this just kind of means the derivative of. Okay, so I'm just saying the derivative of x. If it makes you feel better, you can just define your function x as just x. Okay, so, well, everyone take 10 seconds and do this one right now. I got one.
Me too.
Yeah. So this just says that, well, duh, the function y equals x is just increasing at the rate 1. Okay, so that's kind of a special case of the power rule. So now the power rule, which is what we did last class, we did a derivation that the derivative of x to the n is nx to the n minus 1. Okay, so I'd like to take 5 minutes now and to reprove this rule in a different way, even though that's slightly, maybe arguably a waste of time. I think it is worth it in this case. Oh, and by the way, we proved that this rule, we proved this only when n is a positive integer. Because only when n is a positive integer do I have a binomial theorem which enables me to expand it out, right? And in fact, not only a positive integer, but that n is greater than 1. Because if you think about it, x to the 1, I have no binomial theorem to expand that out, which is why I kind of treated this as a special case, right? Okay, so we did the case when n equals 1 separately. If n is greater than 1, then we did this binomial theorem proof. Okay, so let's try this a different way. Different way. Okay, so it's kind of like this. Okay, so here, the different way is to use the other definition of the derivative, which is oftentimes useful. So the other way of talking about the derivative, as you'll recall, is like, you know, I have some function, and I have some point, and I want to know the derivative at that point, and so I pick an x, and I find the slope of the secant line, and then I do the stuff, right? So in this case, what I'm going to do is I'm going to give you the function f of x equals x to the n, and I'm going to ask, all right, what is the derivative at a? And if I can compute the derivative at a in general, then I'll have a rule for this function. Okay, well this leads to a very different kind of limit. So what is f prime of a by definition? Anyone, you're not writing anything down, so you should talk.
Okay, it's like f of x, or yeah, it's like the y values minus each other, or the x values minus each other. Yeah.
Yeah, of course, taking the limit as x goes to a of that.
Yeah.
Yeah, that's kind of important. Okay, so yeah, that's that. All right, so what we end up with is something very, very different than the proof that we did last class, right? The proof last class involved the binomial theorem, you know, blah, blah, blah. Here, it turns out that what I'm trying to do is the limit as x approaches a of, what is this? X to the n minus a to the n over x minus a. All right, so what's that? All right, you guys have any thoughts about that? How would I compute this limit?
Try factoring.
Yeah, try factoring, right? In fact, if n is something nice like 3, right, let's just suppose that n is 3. So you'd be taking the limit as x goes to a of x cubed minus a cubed over x minus a. Then, in fact, you would just factor it, right? You just factor the difference of cubes. And so what I kind of want here is a formula that works not just for difference of squares, difference of cubes, difference of fourths, but just in general, like difference of nth powers. Is there such a formula? Well, more than just probably.
Binomial theorem.
No, it has nothing to do with the binomial theorem, because no longer are we raising a binomial to some power, but this is like a precalc thing. Nothing? Right, yeah, so, right, x minus a must be a factor of x to the n minus a to the n, right? Because a is a root of this polynomial. And so, just like if you have never seen suppose you want a formula for the difference of fifths, right? Then you can write a function x to the fifth minus a to the fifth, for example, right? Okay, well, I know that f of a is, well, it's 0, right? And my conclusion, based on pre-calc C stuff, is then that x minus a is a factor. In other words, that this function must be expressible as x minus a times stuff. And how do I get the stuff? I can do polynomial long division, or I can do synthetic division. Let's do synthetic division. So x to the fifth minus a to the fifth, let's write the coefficients. There's 1 fifth term, no x to the fourths, no x cubed, no x squareds, no x's, and the constant term is negative a to the fifth. You guys following this? Okay, and I'm going to divide into it a. And if I do that, I get 1, a squared, a cubed, a to the fourth, a to the fifth, 0. So indeed it does go in evenly, and what I've just shown is that x to the fifth minus a to the fifth can be written as x minus a times class. No, careful.
X to the fifth.
That's
X to the fourth.
to the fourth plus a x cubed plus a squared x squared plus a cubed x plus a to the fourth. So that's how you could derive a formula for the difference of fifths. Like there it is basically, right? Okay, so this is just going to work in general. In general, I should always be able to divide this polynomial by this one. Is this all making sense? Okay, so let's actually just do it. But now we have to do a little bit of like hand waving because x to the n, so that's going to be a 1. Then you're going to have no x to the n minus 1s, no x to the n minus 2s. You're going to have basically like a lot of zeros, okay? And then the last one is going to be negative a to the n. So it's kind of a repeat of what we just did, but now we're dividing, it's a little more complicated. So, and then we're also putting in an a. So let's try to be really careful about this. Hopefully it'll work out. So we get 1, then that's a, then that's a squared, a cubed, a to the fourth. And eventually, we're going to get somewhere down here, like a to the n minus 1. Right? And then that'll be boom, boom, and we'll get a to the n, and we'll get 0. All right. So, in computing this limit, I just showed that I can basically, using a sort of algebra fact, that I can factor this polynomial as x minus a times, now I have to interpret that last line. What is that, I guess?
X to the n minus 1 plus 8x to the n minus 2 plus a squared times x to the n minus 3,
etc. until, what's the last term?
a to the n minus 1.
Yeah. Let's see. Are we good? I think we're good. Okay, all of that over x minus a. Okay. So, good. Okay, so then we can cancel, right? And now I no longer have a 0 over 0 situation. Everybody with me?
Yeah.
So let's plug it in then. I can just sub in the a directly. If I sub in the a directly, I get a to the n minus 1 plus, yeah, I get another a to the n minus 1.
Another 8.
And another a to the n minus 1. And in fact, all of these are going to be a to the n minus 1.
Oh, the n of them.
How many of them do I have?
N of them.
I have n of them, yeah. That's not immediately obvious, but just like over here, right? If I started with the 5th degree version, then I have all those guys and also the constant terms. That adds up to n. Yeah, so I have n of these. And so we just showed that the derivative at a is n a to the n minus 1. I don't know, I think that's pretty cool. It is a completely different proof, not based on the binomial theorem. In some ways, I actually like it better because it uses a known algebra fact to convince you that, that the rate of change of any polynomial has to be a degree less. Because in fact, you should already just feel by looking at this limit that the answer is going to be a polynomial, right? Because this goes into this, the derivative of a power function has to be another power function. Okay, that was something that we did. Antares, can you flip around, or is that not possible? Just say it's possible. It's possible. All right, good. So, more. The other thing that is, as promised, I showed that this works only if n is a positive integer. What if n is a negative integer? Let's now compute the derivative of 1 over x to the n. We'll do that. I'll give you a minute. Those of you at home, pause and compute this derivative. And again, if you don't like this notation, if it helps you, you can just define a function to be 1 over x to the n. And of course here I now assume that n is positive. So n is an integer, n is a positive integer. And you can do it either of the two ways, I guess. Are you guys doing it this way mostly? Or that way? Or whatever? Alright, so that's how I started, just like that. What seems like the next good idea?
Common denominator.
Yeah, just get a common denominator. So the limit is h goes to 0 of x to the n minus x plus h to the n all over x to the n, x plus h to the n, and there's also an h. Now, I don't know, what should we do now? Yeah, just do the binomial theorem. I guess, right? I mean, if we got this far, we'll just do that now. So this becomes limit is h goes to 0 of, well, we did this last class, so it should look kind of familiar. X plus h to the n, that's just going to be x to the n minus n choose 1, x to the n minus 1 h. Oh, sorry, that should be a plus. Plus n choose 2, x to the n minus 2, h squared. And we get all the way to second to last term, n choose n minus 1, x, h to the n minus 1, and then the last term is just going to be h to the n. Are you guys with me? All right, all over x to the n, x plus h to the n times h. So it looks actually very much like our previous proof, but just with just kind of a couple extra steps now. All right, let's keep going. So now the negative distributes through, right? And so I get the limit, h goes to 0 of negative, okay, n choose 1 is just n. So negative n, x to the n minus 1 h, minus n choose 2, x to the n minus 2 h squared. These should all be negative, minus, minus, minus h to the n. But now I can divide by h, right? Should have just done that all in one step. I can now divide through by h, and I get something kind of simpler. So the limit is h goes to 0 of negative n, x to the n minus 1, minus n choose 2, x to the n minus 2. Now I divide the h by 1. But, okay, you're kind of seeing where this is going, right? Because now all these terms are going to have an h in them. And so they're all gonna die. You guys following this? I know I'm going kind of fast. You with me? Elmer, with me?
Yeah.
Okay, so now I plug in the 0 for h, and what am I left with? Negative n, x to the n minus 1, all over x to the n times another x to the n, basically. Okay, what is all this crap? Well, this is just, now we just use exponent rules, right? So this is negative n x to the n minus 1 minus 2n, right? X to the n times x to the n is x to the 2n. We okay?
Yeah.
Okay, so final answer. Negative n x to the negative n minus 1. All right, and so what we have really just done is we have shown that the derivative of x to the negative n, where n is positive, is negative n x to the negative n minus 1. In other words, we've showed that it does obey the power rule, right? Even if the power is negative, you can still drop it down and subtract 1. Is this all making sense? I'm not sure this is worth doing after just spending 10 minutes on this. Anyway, there it is. So this rule, so far we've just done things that we already know for the last 15 minutes. We reproved the power rule a different way that hopefully makes some kind of sense. We did a couple derivative rules. Oh, before I erase the board and we move on to something more fun, can we talk about, oh, there's another kind of obvious derivative rule, which I think I mentioned very briefly in class. What is the derivative of the f of x plus g of x function? It's just the same thing. And here you might define a new function h to be, no, that's a bad example. I'm running out of letters. F, G, H, J. You might define a new function j to be the f of x plus g of x function. So that just, it just takes the outputs of the two functions and just, you know, put them together. Okay, so what is the derivative of j? Well, by definition, the derivative of the j function is, well, it's the limit as h goes to 0 of j of x plus h minus j of x all over h. But, of course, what is that? It's going to be j of x plus h is f of x plus h. So it's the limit, h goes to 0, of j of x plus h plus, f of x plus h plus g of x plus h minus f of x minus g of x all over h. Right? This is kind of boring. And then what do? You just split it up into two limits. It's the limit as h goes to 0 of f of x plus h minus f of x all over h, and the limit as h goes to 0 of g of x plus h minus g of x. And note that, why am I allowed to split up those limits? Because they both exist. Okay, so I guess the theorem should be that if f and g are each individually differentiable, then the product is, or then the sum is differentiable, and it's just the sum of the derivatives. Okay, so it's the fact that a derivative is just a limit, and we can split that makes it all work out. Okay, this has been, so far this has been the most boring 20 minutes ever. Couple more things. You had a problem for homework, the derivative of cosine. Should we do that, or is it like kind of chill?
We should do that.
We should do that?
Okay.
We did sine. One class we did it, we did cosine. Should we go over that, or is it just the same proof, right? Yes, Elmer says skip it. Same proof. Okay, so I'll assume that everyone knows how to take the derivative of cosine. If not, you know, we should work on that. All right, let's do a new thing. Yeah, let's do a new thing. Other really, really important function. You may have seen this in the book, and therefore might be a little bit of a letdown. And I have to admit that my proof of this is going to be slightly wishy-washy, but it still is pretty much fine. I want to talk about exponential functions. And I want to specifically talk about the function e to the x. which is kind of like the exponential function. All right, so here we go. Let's take this function, f of x equals e to the x, and I want to compute its derivative. Okay, before I even start, what's e, I guess? Because they better have a good definition of e. What is e?
I think it's equals in D.
No, it is, it is definitely like closer to 3. Yeah, it's like 2.7. Okay, but that's not really a good definition of e. You did this in Precalc B, and then we reviewed it in Precalc C.
Yep.
Compounding continuously.
Compounding continuously, yeah, or something like that, right? In fact, here's E. This is just a sort of a 1-minute recap. We derived very carefully this formula which said that the amount of money in my bank at any particular time is the principal times 1 plus the interest rate over the number of times per year that I compound to the nt, right? You did this in Precalc B, you also did this with me. Okay, and then what we did is we took $1 at 100% interest for 1 year, and we looked at what happens upon different compoundings, okay? And if you compound once per year, you end up at the end of the year with $2, because 100% interest. But if you compound, like, I do the same problem over and over again, so I know this by heart. If you compound twice a year, you end up with like $2.25, et cetera, et cetera. If you compound n times per year, then the amount of money in your bank is going to be principal 1 times 1 plus the interest rate, which is 1 over n to the n times 1. Okay. So that's kind of the formula for the amount of money I'll have in the bank if I compound n times per year with $1, 100%, just 1 year. And what happens is if you let n go to infinity, then you get e. Right. Okay, so bye, go away. Now, go away.
My stuff here.
No, said go away. Thank you. Okay, good. All right. That was some jerk. That's what. Okay. All right. So basically, here's our definition of E. E is what you get when you take the limit as n goes to infinity of 1 plus 1 over n to the n. Okay? And if you think about this for a minute, it's not obvious that this should be any particular number like 2 or 3 or 5, but I think it is kind of obvious that it's not going to infinity or 1. If you think about this, normally when you raise numbers to bigger and bigger and bigger powers, they get bigger and bigger and bigger, right? But it's also true that if you raise 1 to a power, then it's not getting very big at all, right? So as n goes to infinity, I'm taking a number which is closer and closer to 1, and I'm raising it to a higher and higher power. So it's like that n is trying to make it get really big, but this n is making the inside of the parentheses get really, really close to 1, and so there's some balancing act, and it ends up to be, for mysterious reasons, like 2.73. I never would have been able to just predict that by thinking. All right, so that's our definition of E. It came from Precalc B. There is an alternative definition of E, and you get the alternative definition of E when you do the limit flippy-flippy. So let's let A be 1 over n, for example. As n goes to infinity, what does A go to? Okay, it goes to 0, of course. 0 plus, okay, whatever. So I might alternatively define E as the limit as A goes to 0 plus of 1 plus A to the 1 over A. So that is also a perfectly legitimate alternative definition of E. Okay, without further ado, let's take the derivative of this exponential function. Okay, let's do it. Oh, how do we do it? I don't know. Same thing we do every single time, right? It's just the limit. H goes to 0. F of x plus h minus f of x all over h. Well,